Good morning.
Morning.
Today's lecture we will start on chapter 8, which is the electrical power system. So what we discussed in previous chapters are related to circuit analysis, or how to solve some circuit problems, or basically I would say like the ABCs of electrical engineering, or basic ABCs. Then we start doing some analysis, like creating some words that have meaning. Now, we would like to use these words as a sentence, as a useful sentences. In other words, we would like to use what we have learned before in electrical engineering, fundamental electrical engineering course, as an application more than as just a circuit without knowing what's this circuit. So, previously, when we did the first and second exam, we used to have a circuit and we don't know what it is, or how can we use this in real life. Now, we will try to model some practical things that we have, some devices, like a motor, a transformer, for example, as we'll discuss later, like operational amplifiers, different types, generator. So we will see how we can model this to find an equivalent electrical circuit model. After that, we can use this in real life for, or we can apply the circuit techniques that we learned before, KVL, KCL, Ohm's law, power analysis, complex power, real reactive power, all of these concepts that we learned. Now it's time to use them for some useful applications. So for chapter 8, it's electrical power system, we will go first through the three-phase system. So the three-phase system is basically same circuit technique analysis that we know, but we will apply it for multiple phases, or something we call a three-phase, which is basically we will apply the same context, but now times 3. Then after that, we will go to the transformer. Then we will start discussing the motors. That's the plan on chapter 8. Okay, so what does three-phase system mean, or polyphase system mean, and what's the importance of using this? Okay, when we are, or as we know from circuit analysis, and even like in previous lecture, the electricity that connected to our home, or electricity that we are using it, are based on AC, right? So we have the AC power at the frequency 60 Hertz. It's most like cosine waveform. And the magnitude, it can be either 120 or 240 that's connected to your home. While in the distribution area, it can be like for 7.2 kilovolts. It can be for medium voltage as 11 kilovolts or 12.47, whatever, and we have high voltage like 115 kilovolts, 230 kilovolts. So we have high voltage, we have something we call it extra high voltage, 400 and above. We have high voltages between 400 to 100. We have low voltages, I think it will be between 60, medium voltages between 66 volts up to 12, or I would say 33. Then we have the low voltage of 7.2 kilovolts and below. That's overall for the power system. And we say the power system is the electrical system connection that we connected to our utility, our electrical utility. Then, as we know, the power is a function of both currents and voltages, right? So the overall power system, we're going to assume the voltage is constant. So when we are dealing with the residential, like with the wall plug, the power or the voltage is fixed, 120 volts. And as we discussed last lecture, the power connected to your home is either 120 or 240. I'm sorry, the voltage is connected there. So whenever you look at the voltages, it's fixed, it's constant. Every time we assume the voltage is known as 120, 240, or if you are industrial load, 480, etc. So whenever we are dealing with any type, we will assume the voltage is known. So when we go to the power lines, and if you know that type, what's the power line, or then you know what the voltage is. For example, 132 kilovolts. What's the thing that we don't know is the current. Why we don't know it? Because the current depending on the load. We know as the relationship between, again, the power, S bar equals V bar times I bar conjugate, right? So V is constant. So we will realize that S bar is directly proportional to the current, right? Let's talk about the magnitude. Yes, that's what we have in the math. Then, when we increase the amount of power, this means we will increase amount of currents. The currents we don't know, or the current is changing depending on the load. The load in the morning is not the same as in the afternoon. It's not the same at noon. It's not the same at evening, right? It's changing. Therefore, the current will be changed depending on the load status. So, most likely, again, we will assume the voltage is known. Then the impedance it can be like also changing depending on how many devices are connected. Then most likely the larger loads or the larger power consumption, the larger currents will be. So this can do some limitations on us. Also recall last lecture when we talked about the AWG. AWG 10, it can handle 30 amperes, AWG 12, 20 amperes, something like that. So AWG means each wire or each conductor has its own ampere capacity. And that ampere capacity, if we exceed this, this will cause overheat for the conductor, and that overheat will cause damages, sometimes causes fires. So we don't prefer to make an overload for the conductors. Then there is an ampere capacity. So there is some current capacity, current limits for each conductor that we cannot exceed. So let's talk about then, as I mentioned, like in residential home, we have 20 amperes or sometimes 30 amperes. Then this is something also you can imagine it as the water pipelines. If there is a large demand of the power of the water pipelines, you need to have a larger thickness, right? Replace that pipeline by a larger thickness. Increase the radius, then you can have more water, right? Or you can install another water pipeline to supply your demand. So now the concern is, yes, power is directly proportional to the currents, but I cannot increase the current forever. I cannot say, okay, I need more power, let's increase the amount of current as much as I want. No, because there is a current capacity. So let's assume we have two conductors like this way. We have phase or that voltage source connected to the load. Then we have two conductors, live and neutral, as we see in this diagram. And assuming the ampere capacity, which is again, S is directly proportional to I, let's assume that after doing several calculations, this conductors can supply only 1 kilowatts as a roughly number. So let's assume after several calculations we can, for this system, the maximum power that we can get is 1 kilowatts. Assume that load is 2 kilowatts, not 1 kilowatts. What should I do to supply that load? What do you think? I want to hear from you. What do you think? How can I supply a 2 kilowatts load while the system, the conductors that I have are based on 1 kilowatts? Any thoughts? Yes?
Add another wire in parallel.
Add another wire. That's a great idea. So we can basically, I would say, like, we can divide the loads into 1 kilowatts, then add another wire. Is there any other idea? Oh, this is a great idea. Is there any other? How about, yes? Yeah?
Go to the next step up in the voltage.
Increase the voltage
The next, like,
to the next level. That's good, but the thing which is assume the devices that you have are based on 120 volts or 240 volts. So increasing the voltages will not be compatible with the devices with the load. So increasing the voltages is good, but unfortunately it will be incompatible with the devices. So yes.
increase the wire diameter.
Increase the wire diameter. That's another approach. Which is, again, you can imagine this, that you need You are supplying your home by water, and you have a large demand of water. So there is one way by connecting a new line, a new water line, new water pipelines, or increase the diameter for the water pipelines connected to your home. So economically, removing the existing one and adding a new one with larger diameter might be expensive. And the other thing, which is the overall hit cost, which is basically you are connecting the power lines based on the infrastructure of the towers, the infrastructure of even the weights of the wires. So if you increase the thickness, this will increase the weights, will affect on the mechanical structure of the towers. So it can be very expensive because we need to modify all of the power lines, all of the power lines, utility poles. We need to modify them so it can handle that large amount of thickness. So yes, also it's a good idea to increase the thickness, but unfortunately it will be very expensive. So we realize here so far the best thing to get 2 times double the amount of the power by doubling the amounts of the circuits. Doubling the circuit, or in other words, by doubling the costs. Is this correct? Yes? That's what we have. Now let's assume, or let's think about it. Is there any other economical solution than doubling the power, doubling the costs? Can we find a way to make it more cheaper than that? Yes, we can. How? This is positive, this is negative. This is positive, this is negative. Can we make a common negative? Yes, we can. So, that's what we did here. And instead of doubling the circuits, we can have a common neutral or common returning currents, 2 life. So the first life we'll call it phase A, second life phase B, and the neutral is the common. What's the advantage of it? We have 3 conductors, so basically 1.5, 1.5 times the cost will yield to 2 times the power. Which means I can save more money, right? Yes, it seems here, which is I have 3 conductors and 3 conductors. And instead of using 4, I'm going to use 3. And here I'm doubling amount of the power by using 3 conductors. And when you connect this for very long distance, for 100 miles, this means you're going to save a lot of money, right? Then this thing is called 2-phase or polyphase or biphase. Biphase, which is basically phase A, phase B, and the neutral. But when we look at biphase, can we find a cheaper option than that? That's another question, or that's another way of thinking. So, can we find a cheaper? Okay. How can we find something cheaper than the biphase? Biphase 1.5, 1.5, the cost will double the power. So the answer, yes, we can find, and it is based on the 3-phase. Okay, what does 3-phase mean? So in 3-phase, we can say we can have 3 conductors and 1 in neutral. So this is phase A, phase B, phase C, and 1 in neutral. So all of these phases are positive and the neutral is negative. So 1 returning currents and 3 positive currents. So 3 conductors. So here is the load side, here is source, here is the load side. So we realize that we can have 4 conductors. Then we will get 3 times the power. Okay. In other words, 2 times the cost will give us 3 times the power. So this is even much cheaper than when we talked before at the biphase. 1.5 costs times the cost will yield to 2 times the power. Just increase another half cost, then you can triple amount of the power, which is something great, right? Then that's the three-phase. So we realize the three-phase, it's even cheaper than the single phase. I'm sorry, the biphase. Biphase, cheaper than single phase. But three-phase is even cheaper than that. Okay. Now, with this situation, we will assume a phase shift for each phase. So the phase A, we will assume the angle of phase A is 0 degrees. The angle of phase B is negative 120 degrees. The angle of phase C, positive 120 degrees. Why we assume these angles? Basically, I will say it is 360 divided by number of phases. So 360 divided by 3, this yields 120. So the phase shift between phase A and B and C, there should be 120. Again, we will discuss this later, but here just for your information, we choose 120 as a phase shift. Again, we will discuss in details later today's lecture or maybe next lecture. So we just keep in consideration that the phase shift between each phase is 120 degrees. The magnitude of the voltage will be the same. If it's 120, all of these phases 120, but phase shifts 10, the other one 180, the other one negative 120 and negative 120. Now, with the three-phase, we found the life is much easier. So we can connect 3 times the power by doubling the cost. And even we realize when we connect the power for, we call it transmission lines and high voltages, where we will not connect the load. If we connect if you distribute or if you transmit the power from one side to the other side, and there is no connection, no overlap connection, basically during the high voltage scale, we can avoid or we can get rid of the neutral and we can use only 3-phase alone. We can say that let's use phase A, B, C without neutral. We will discuss also this approach in deep details, how to avoid using the neutral, but I'm just telling you about the technology now, and as an overview, then let's go into details. So basically, we realized in 3-phase, we can use 3 positives or 3 conductors to supply the power, and we don't need to have a neutral. This means we can save more money, right? Then the 3-phase works great. This one works great. Now, one more question. Is there any cheaper option than the 3-phase? Get back to 4-phase. We prefer to use odd numbers, so we can. I would say 5-phase. Can we replace the battery? Okay, so we have cheaper option than 3-phase. 5-phase. Again, we prefer to use odd numbers. 5-phase, 7-phase, 9-phase, etc. So we have 5 phases, and that 5 phases we will have 5 conductors. 1, 2, 3, 4, 5. Phase A, B, C, D, E. Then we have the neutral. And the phase shift 360 divided by 5. Then you can determine the phase shift between each one. Okay. In 5-phase, we have 5 positive and 1 returning current for the negative, for the neutral. So 5 phases means we have 1, 2, 3, 4, 5, 6 conductors, then 5 times the power. Or in other words, 3 times the cost, you will get 5 times the power. Then this means this also we can save more money more than the 3-phase, right? Now the question is, our electrical utility, is it based on single phase, biphase, three phase, five phases? Three phases, right. So why? We just said that five phase is better. Why we use three phase, why not five phase? Yes?
Because we don't really need 5-phase. None of the stuff that we operate is going to be consuming that much power.
Sometimes we really need like much power. But I would say like, let's think about it in economical solution. So here in mathematics, we see like 3 times the cost equal to 3 times the power based on the conductors. But do you think this is the only solution? I mean, this is a good approach to say 3 times the cost based only on the conductors? Okay. Let's think about the power lines, where we have a large utility poles, or a large towers. So are you familiar with these towers, these big towers, right? So these big towers are based on the three phase. Okay, so you see they take a large size, and this is based on three phase. If we have 5 phases, this means we will have a larger power size, power tower size. This tower, if it is going to be larger and larger and larger, this means the overhead cost in building that tower. You need to have more steel, you need to have more concrete on the bases, you need to have these kind of towers, they need to have a large thickness or a large capability of handling these loads. So I think, I mean, some of you are mechanical engineering and you know about the loads more than me, which is how can we handle the weights, how can we handle or the overall structure. So basically, when we have 5 phases, this required a very expensive tower to build, which is way expensive than the 3 phase. So we realized, okay, 5 phase can provide higher power, but the overall cost, 3 phase will be cheaper. So the benefits that we will have from 5 phases will not be significant. And in the same thing when we build the transformers, building the transformer based on 5 phases requires a very large size transformer, and this will be a big challenge. So in summary, theoretically, 5 phases is better than 3 phases. But practically, unfortunately, we cannot do that, which is very expensive. Now, we see some applications are based on 5 phases machine for only research and development. So you can see, especially on some industrial loads, we have some 5 phases induction motor. 5 phases, some part of motors. Those are for research and development, but they are not actually practically applied. I mean, you might have some, or you might see a lot of research about it, but we are not using it in real life as commercial thing, or like sell thing, or let's say, let's use this in real life, or let's use this in production line, etc. So again, 5 phases, we are using even like some small grid connection for 5 phases, only again under research and development, but we are not applying it for overall life, because when we have a big towers, big infrastructure, big costs, and also we need to purchase a big land for these towers to supply the load. So we realize that 5 phases is not applicable because of the size, the cost. Okay? Now, is there also theoretically cheaper option than the 5 phases? 7 phases. If you keep up, you will get larger amount, 7 phases, or 9 phases, 11 phases. When you keep up, again, theoretically, we will realize we will save more money by tripling or double or 5 times the power, 7 times the power, 9 times the power, etc., by saving more costs. But unfortunately, the problem is all of this cannot be applied. Okay? How to apply this. So we realized the optimal solution, so we can save more power with lower infrastructure costs as a trade-off. We realized the optimal solution is the 3-phase. That's why the existing system is based on 3-phase. Then we realized that the 3-phase is working great. And actually also the 3-phase has been invented by Nikola Tesla as well. And Nikola Tesla, when he invented after he invented the AC and wins, and remember when I told you about the war between AC and DC, AC wins. Nikola Tesla didn't stop and say, okay, I win, and that's fine. He keep inventing more by inventing the three-phase, and he said that the three-phase also, we can save more money by tripling amount of the power. Then this makes also the AC more dominates. Then we all of the infrastructure of the power system is based on the three-phase. That's why we have here all over the whole world, not only in the States, and it's in every country in the world. It's based on the three-phase system. Okay. Any question about this overview? Yes.
So is it always on, so we always have one neutral wire?
Yes, one neutral wire. Then again, the phase shifts between any phase will be 360 divided by number of phases. So 360 divided by 7, 360 divided by 9, 360 divided by 11, etc. That's how we determine the phase shift. Any other question before start going to the three phases? Okay. Now, since the existing power